Well, I've mentioned the Chinese remainder theorem often enough in the previous presentation that now it's about time to actually take care of proving the Chinese remainder theorem, so let's get to it. Basically, we will start with linear congruences, and well, on one hand, we could say that linear equations, namely equations of the form ax plus b, are the simplest type of equations that we can ever encounter anywhere. And we will consider what happens when equality is replaced with congruence modulo m, and that's going to be the first part of the presentation. We will also see how the solution of several very simple equations of this type leads to the Chinese remainder theorem, and that one is important because it paves the way for efficiently working with large numbers. And we will conclude with some results about numbers of the form 2 to the n minus 1, because those are then often used as the moduli in computer arithmetics. Well, let's get started. We're starting fairly simply, namely we are looking at a modulus m. We take two integers a and b, whose so that the greatest common divisor of a and m is d, and we claim that the congruence ax equivalent to b modulo m has no solutions if and only if d does not divide b. And in case d divides b, the congruence will have exactly d solutions that are pairwise not congruent modulo m. Okay, well, we're first noting, and that's something that we'll need for both directions, that, well, because d is the greatest common divisor of a and m in particular, d divides a times x for all integers x. Okay, we're going right to left, so we are assuming that d does not divide b. Well, if d does not divide b, then d does not divide ax minus b, because d divides ax, and so if it were to divide that difference, it would also divide b. Okay, now because m is a multiple of d, this means that m does not divide ax minus b either, because after all, if m were to divide this difference, then d would divide it. And that means when d does not divide b, the congruence ax equivalent to b modulo m has no solutions. Okay, for the other direction, we're going to prove the contrapositive, so we let d divide b, and we let a prime to be a divided by d, which works because d is the greatest common divisor of a and m. And we let b prime be b divided by d, which works because d divides b. Well, then the greatest common divisor of a prime and m is 1, and that means by an earlier result that a prime times 1 minus b prime all the way through a prime times m minus b prime is a complete set of residues modulo m. And that means in particular there is a k so that a prime k minus b prime is equal to 0 modulo m, and that means that the congruence has a solution, and that means we have proved the contrapositive. If d divides b, then there is a solution. And yeah, I think now we're just going to write it down, because then ak minus b, yeah, is a prime k minus b prime times d, because we're factoring out the d. Yeah, and that's 0 times d, and that's 0. I jumped the gun a little bit here. Again, because this means a prime k is equal to b prime. It doesn't mean ak is equal to b. But if we're looking at ak minus b, then we can factor out d out of a prime, and we can factor d out of b prime, and a prime k minus b prime is 0, and 0 times d is 0 modulo m, and that means we've got a solution. Okay, now finally we continue. This is going to take a little bit longer here. Let m prime be m over d. With k from what we had, so that ak minus b equivalent to 0 modulo m, we have that any k plus n times m prime is a solution of ax equivalent to b modulo m, because a times k plus n m prime is ak plus a prime d in m prime. Good grief, and the ak is okay, and we try to finagle a b into that somehow, I think. So that's ak plus a prime in m, and that's because dm prime is m, and that is ak. and AK is B modulo M in the last two steps, and so that means that those things are all solutions. So not only do we have one solution, we have multiple solutions. Now we have to see which ones are pairwise incongruent. And well, for any ij playing the role of k between 0 and d minus 1, these solutions are pairwise incongruent modulo m. And that is because for I less than or equal than j, we will have that k plus j times m prime minus k plus I times m prime is j minus I times m prime, and with j minus I being between 0 and d minus 1, that number is not divisible by m unless it is 0. And now on the other hand, so we have these pairwise incongruent solutions, so we have at least d pairwise incongruent solutions. Now we have to show that we have at most that many. Well, for any n in the integers, still playing the role of this n here, which is this n here, for any n in the integers, there are a quotient and a remainder j, so that n is qd plus j, and then we have that k plus j m prime minus k plus n m prime. Well, that's j m prime minus qd m prime minus j m prime, right? So we canceled the k's and replaced n with qd minus j and multiplied out the parentheses. Well, that is negative qm, and that's because jm prime minus jm prime is gone, and d times m prime is m, so that's negative qm, and that is divisible by m, which means all numbers of the form k plus n m prime are congruent to a number k plus j m prime with j between 0 and d minus 1. And if we now conclude that proof, so now we have that the numbers of the form k plus n m prime are all solutions, and there are d of them that are distinct. So finally we have to show that anything else does not solve the congruence. So if we take a number k plus n m prime and we add a remainder greater than 1 after division by m prime to it, then we realize that that is not a solution, because a times k plus nm prime plus r, well, we multiply that out, that's ak plus a times d in m prime, a prime, right, a is a prime d plus times n m prime plus a prime d r, and that's a k plus a prime n m, because d m prime is m, plus a prime d r, and now we can get rid of the m at least, right? So that's equivalent to ak plus a prime dr, and a prime d is a, right? So ak is b modulo m, that's right, and we keep the a prime dr, and that is not equal to b, and that's because a prime dr, that's ar, and that's not equal to 0 modulo m. And so that means that the numbers k plus j times m prime with j from 0 to d minus 1 are all pairwise incongruent solutions modulo m. Okay, you probably noticed that I paused for a minute here because I wanted to double check why a prime dr is not equal to 0 modulo m, and that is because the a prime doesn't have any common factors with m. D is of course the greatest common divisor of a and m, and r is less than or equal to m prime, which means there is no way I can piece together a factor m out of the factors of d and r, because a prime is no help, and so that means this one here is not divisible by m, and that means that this really is not equivalent to b modulo m. Okay, sorry for the hiccup here. These kinds of things can take a long time sometimes, and well, it did at this stage for me at least. Okay, corollary to the solution for linear congruences is that if we have a modulus m and AB are integers, and A and M are relatively prime, well then AX equals B modulo M has a unique solution modulo M, and that's because D is 1 in the previous theorem. We define now when M is our modulus and A and B are integers, if A and M are relatively prime, then any solution of AX equivalent to 1 modulo M is called an inverse of A modulo M. Okay, I didn't need the B here, but technically this is still correct. An inverse is a multiplicative inverse of A is just something so that A times the multiplicative inverse is equivalent to 1. So this is the kind of thing that works in modular arithmetic that definitely does not work in integers, because after all, in integers, any two integers that you multiply together, unless they're both 1 or both minus 1, don't give you 1 as a result. Okay, as an example, we're going to solve a congruence. We're going to solve the congruence 215x equivalent to 86 modulo 301. And what we're going to see is that the procedure is very similar to what we just did in the proof. Namely, we first note that the greatest common divisor of 215 and 301 is 43, and that is because 215 is 5 times 43 and 301 is 7 times 43. And another way to work that out is to just use Euclid's algorithm, or go back to the presentation that we did on Euclid's algorithm, because there we saw that 43 is 3 times 215 plus negative 2 times 301. I'm not going to, well, actually I can double check that really quick, right? Because 3 times 215 is 645 minus 602 is 43. Yeah, sure. Okay, so because 43 divides 86, which is the right-hand side, that means there is a solution, and in fact we know from the previous results that there are 43 of those things. Okay, so let's take a look at the congruence 5k equals 2 modulo 301. And we are doing that because when we solve 215x equals 86, the first step is that we're going to go to the a prime and the b prime, right? So we divide out the greatest common divisor, and 215 divided by 43 is 5, 86 divided by 43 is 2, and so now we have a solution which is k equals 181. That's exactly the k from the proof. And so now with m prime being 301 over 43, which is 7, the numbers k plus j times m prime, which is 181 plus 7 times j going from 0 to 42, are the solutions that are pairwise incongruent modulo m. Okay, so that means the proof that we have there for the solving of these very simple linear congruences is entirely constructive, and it's certainly shown very nicely here in this example. Okay, now if we have a prime modulus, well, or mathematicians in general, when we talk about inverses, it's always interesting to know which numbers are their own inverses, and it turns out that here, at least, even though inverses don't exist in integers, this result is analogous to the result for integers, namely an integer a is its own inverse modulo p, if and only if a is equivalent to 1 modulo p, or a is equivalent to negative 1 modulo p. The proof, well, there's one direction that is trivial, because if a is 1 or a is minus 1, you square it and you get 1, and you get that modulo p as well as in the regular integers, so we only need to focus on proving the other direction. So we let a be a number between 0 and p minus 1, so that a squared is 1, so that a is its own inverse modulo p. Well, that means that p divides a squared minus 1, and a squared minus 1 is a plus 1 times a minus 1, and that means that p divides a plus 1, or that p divides a minus 1, potentially both, but certainly p can't be split because p is a prime number. Well, because p is prime, that's not possible for a plus 1 being 0 or p, or a minus 1 being 0 or p. And if a plus 1 is 0 or p, well then a plus 1 must be 0. And well, actually, if a plus 1 is 0 or p, then either way a is negative 1 modulo p. And if a minus 1 is in 0 or p, then a is equal to 1 modulo p either way. And so that concludes this little result. Now we're going to prove the Chinese remainder theorem. We're going to solve individual linear congruences, and then we're going to solve multiple linear congruences. And before we do that, we also need a quick result that shows us how to go between different moduli. Namely, if we have two moduli k and n that are relatively prime, and a and b are integers that are equivalent modulo k and modulo n, then they are also equivalent modulo k times n. And that is in preparation for what we're going to do in the Chinese remainder theorem, where we have several congruences modulo different moduli, and we want to have a congruence modulo the product of the moduli. So how do we prove that? Well, if they are both equivalent modulo k and modulo n, then k divides b minus a and n divides b minus a, and k and n are relatively prime, which means that none of the prime factors for k occur in n and vice versa, so that means k and n divide different parts of the prime factorization of b minus a, and that means that k times n divides b minus a, and that means a is equal to b modulo k times n. Okay, we ought to get, finally we have the Chinese remainder theorem. And we take k different moduli, pairwise relatively prime, and we claim that for any integers a1 through ak, there is now an integer x, so that x is equivalent to aj modulo mj, so that holds for all the k. And moreover, and that's really the important part now, this number is unique modulo the product m1 through mk. Because what that means is that we can take comparatively small numbers, namely numbers that don't exceed the largest of the moduli mj, and by just saying that these numbers now represent stuff, that these numbers aj represent a number x, we realize that they represent a unique number x modulo the product. So if I've got 10 moduli that are all at least 10, then I can represent numbers up to 10 to the 10, namely 10 multiplied with itself 10 times in the mj's, by just solving x equals, by just finding the solution aj equal x for that integer x between 0 and something around 10 to the 10 or so, and we do that with 10 numbers aj that are all fairly small. Proof of the Chinese remainder theorem, well, we first work it through for k equals 2. And, well, if you've got two moduli m1 and m2 that are relatively prime, then I can solve individual equations, but now here we have to make sure we keep track of the indices. So there's a number y2 that is the multiplicative inverse of m1, because we say that m1 y2 is equivalent to 1, but it's modulo m2, right? So m1, because it is relatively prime with m2, has an inverse modulo m2. Similarly, m2, of course, has an inverse modulo m1, because m2 and m1 are relatively prime, and we call that inverse y1. And now, the x that we have, that solution, is just a1 m2 y1 plus a2 m1 y2, and that is because if x is a1 m2 y1 plus a2 m1 y2, I think we'll first go modulo m1, and modulo m1, this thing here is 0, and modulo m1, this thing here is 1, which means that x is equal to a1 times 1 plus 0 modulo m1. And if we're looking at x again and look at it modulo m2, we realize that this here gives us 0 modulo m2, and this here gives us 1 modulo m2, so this is 0 plus a2 times 1 modulo m2, so that means that x is a solution. And in the general case for the existence, because the mj are pairwise relatively prime, for each j there is a yj, so that the product of all the mi except for mj, that is important. That product is relatively prime to mj, which means it has a multiplicative inverse yj. So there is a yj, so that this product times yj is equal to 1. And we can let x be just the same as before. We take it to be the sum of all the aj times this product, which with respect to the right modulus turns out to be 1, right? So this is this other trick in mathematics that sometimes you have to multiply by 1. So with this x, for each n between 1 and k, we have that x is the sum j equals 1 to k, aj times the product I not equal to j, mi yj. And if we now split off the nth term, we have an times the product I not equal to n, mi yn. And of course, that product here, right? Okay, the product of the numbers n, so the yj is not raised to a power here, so this is just 1 yn we have here. So that means that this product here is 1 modulo mn, and all the other ones, because j is not equal to n, I does not skip n, so there's an mn here, which means that this stuff here is 0 modulo mn, and that's exactly what I'm saying here. An times 1 plus sum j not equal to 1, aj times 0 times yi, which is an modulo mn. So that means we have a solution. Well, we also need to prove that the solution is unique. So if x and y are two solutions, then x is equal to aj is equal to y modulo all the mj's. That means that mj divides x minus y for all j, and because the mj's are pairwise relatively prime, we conclude that the product divides x minus y, and that means that modulo the product of all the mj's, the solution is unique, because if we have two of them, then they are equivalent modulo that product. Okay, now the Chinese remainder theorem, the proof of the Chinese remainder theorem also is constructive. So if we want to solve the system of congruences where x is equivalent to 1 modulo 5, x is equal to 4 modulo 7, and x is equivalent to 2 modulo 9, well, then we take those extra products, right? We take 7 times 9 times y1 equal to 1, and the solution of that is y1 equals 2, and that's because, let's see, 9 times 7 is 63, times 2 is 126, and 126 is 1 modulo 5. 5 times 9 times y2 is equivalent to 1 modulo 7, for y2 being 5. And that's because 5 times 9 is 45, times 5 is 45 times 5 is 90, plus 45 is 135, and 135, 130, let's do that again here. 5 times 9 is 45. Times 5 would be 45, 90, 180, 225, yes, 225, and 225 is 210 plus 14 plus 1, which means it's equivalent to 1 modulo 7, yes. Okay, I didn't get my multiplication right at first here. And 5 times 7 times y3 equivalent to 1 modulo 9 is solved by y3 equals 8. Well, let's see about that. 5 times 7 is 35, times 4 is 70. 70, let's do it again. 5 times 7 is 35, times 2 is 70, times 4 is 280, and 279 is divisible by 9, so this really is equal to 1 modulo 9. How did I solve those? Well, basically, I just started counting by 63, counting by 45, counting by 35, and computing moduli, and that will give me the solution in at most 5 steps. in at most 7 steps, in at most 9 steps, right? And so then we set the x equal to exactly what we had in that proof, namely 1 times the 63 times the 2 plus 4 times the 45 times the 5 plus 2 times the 35 times the 8. And when you work that out, that's painful. Okay, if you do the numbers one by one, it's not that bad. 2 times 63 is 126, sure. 9 times 20 times 45 is 900, yes. And 8 times 70, that would be 8 times 7 with a 0 at the end, that's 560. And so then that would be 1026, 1586. And that is the number. And now, of course, if we want to get the modulus modulo 315, that ends up being 11. And that is because 5 times 315 is 1575. Yes, sure. Okay, so that shows how to solve these things and how to get the solution as a number modulo, as a small number modulo 315. Okay, the way you do that is exactly the way I've done it here, and of course for larger numbers you would use a calculator, right? So that's the solution, and that's the end of the example. Okay, so how do we now do arithmetic with large integers? Well, we take pairwise relatively prime numbers m1 through mk, and every integer between 0 and the product of m1 through mk minus 1 is unique modulo the product of m1 through mk. And that means to uniquely represent integers up to size capital N with smaller integers, we would have to find pairwise relatively prime integers m1 through mk whose product exceeds n. And numbers x up to that capital N are now represented by the tuple x1 through xk of their least non-negative residues modulo the mj's. Because after all, we would just say that x1 is equivalent to x modulo m1, x2 is equivalent to x modulo m2 all the way through xk. The arithmetic is done component-wise because now we have a vector here, and we would do arithmetic component-wise. That works because arithmetic works out okay modulo every single modulus. And well, on parallel computers we can do these operations in parallel, and thus the operations would take the same amount of time as a regular operation. We would just need as many processors as we have residues. So that turns into a very fast arithmetic for large numbers as long as you've got a parallel computer. And it turns out then computer arithmetic modulo numbers of the form 2 to the m minus 1 is then particularly efficient, because if we store the number in the lowest m bits of a signed or an unsigned integer, then we would wrap around to 0 when all the lowest m bits are 1, which means, of course, that carryovers and things like that must be handled differently than the default. We're not going to discuss that here, how that goes. But this is still easier than using other moduli, because for those you would have an even worse number to identify for the carryovers, right? Now you could, of course, say working with moduli of the form 2 to the n would be even easier, but that's out of the question because those are not relatively prime, and that means that they are useless as moduli for the Chinese remainder theorem. So here we have to merge what nature gives us with what can be implemented on computers, and that approach apparently is the happiest marriage that people could find for these two things so far. And what that means, however, is that we are interested in relatively prime numbers of the form 2 to the n minus 1, because those are the most efficient moduli that can be used with the Chinese remainder theorem. Alright, so we're going to look at these numbers, and we start with a lemma. We take a and b to be natural numbers, and we let r be the least positive residue of a modulo b. Then the least positive residue of 2 to the a minus 1 modulo 2 to the b minus 1 is 2 to the r minus 1. Well, once you have that idea, to prove it shouldn't be that bad, because if a is qb plus r, we get 2 to the a minus 1 is 2 to the qb plus r minus 1, which is just working with powers 2 to the r times 2 to the b to the q. And 2 to the b is equal to 1 modulo 2 to the b minus 1. So this ends up being 2 to the r times 1 to the q minus 1. And that's 2 to the r minus 1 modulo 2 to the b minus 1, of course. And that is already the proof. Now, with respect to the next theorem, notice that the least positive residue of 2 to the a minus 1 modulo 2 to the b minus 1 is also the remainder of what you get when you divide 2 to the a minus 1 by 2 to the b minus 1. That's obvious, because the least positive residue is just the remainder of the division. Similarly, the least positive residue of the division of a by b is this remainder here. Basically, and this is then what is the key to the next theorem, is that when you do arithmetic with the 2 to the n minus 1s, there are certain operations that are basically reflected in the exponents, because after all, even though the results are not exact, the remainder of division of 2 to the a minus 1 modulo 2 to the b minus 1 has the same remainder in the exponent as we get from the division of a by b. And that is the key to the next result. Namely, if x and y are natural numbers, then the greatest common divisor of 2 to the x minus 1 and 2 to the y minus 1 is 2 to the greatest common divisor of x and y minus 1. And the proof is then surprisingly simple. Assuming that x is greater or equal than y, we're just going to run the Euclidean algorithm. And the first step in the Euclidean algorithm applied to 2 to the x minus 1 and 2 to the y minus 1 is that 2 to the x minus 1 is sum q times 2 to the y minus 1 plus 2 to the r minus 1. And that is exactly from the previous lemma, the when you take 2 to the x minus 1 and divide it by 2 to the y minus 1, that lowest positive residue, that modulus, that remainder is 2 to the r minus 1. And we realize that from the previous lemma, r is the remainder of the division of x by y. And so that means, with a quick induction, that the numbers in the Euclidean algorithm for 2 to the x minus 1 and 2 to the y minus 1 are of the form 2 to the k minus 1, and the exponents are the numbers we get in the Euclidean algorithm for x and y. And that means the algorithm for 2 to the x minus 1 and 2 to the y minus 1 stops at a positive integer, so that 2 to the x minus 1, that the greatest common divisor of 2 to the x minus 1 and 2 to the y minus 1 is in fact 2 to the n minus 1. And that number n, because the exponents are obtained from the Euclidean algorithm for x and y, that number n must be the greatest common divisor of x and y. And that is already the proof. And I've actually, as I set up the slides, struggled with this one quite a bit, but once you see it all, and once you see how everything fits together, it is quite beautiful, because basically you're pawning off all the ugly stuff for the powers of 2 to the n minus 1. You pawn that off into operations for the exponents, which are then, of course, easier than first dealing with powers. Okay, so as a theorem then, when x and y are natural numbers, then 2 to the x minus 1 and 2 to the y minus 1 are relatively prime, if and only if x and y are relatively prime. And that's because by the preceding lemma, they are relatively prime if and only if their greatest common divisor is 1, and the greatest common divisor is 2 to the greatest common divisor of x and y minus 1. But 2 to the greatest common divisor of x and y minus 1, that's equal to 1 if and only if the greatest common divisor of x and y is equal to 1, and that is the case if and only if x and y are relatively prime, and that is the result already. So that means that there are many reasonable numbers of the form 2 to the n minus 1 that we can use in an implementation of an arithmetic that relies on the Chinese remainder theorem. We just start with small numbers that are relatively prime, and I'm not sure what's more effective, if we should use just the prime numbers, or if we should use certain kinds of prime powers 2 to the n or so. But that is something that is then certainly left to the individual implementation. And it is then actually a pretty neat exercise to find a set of numbers in sub j that are preferably all smaller than 64 that can be used in arithmetic that models 200 decimal place arithmetic. Why do I want those numbers to be smaller than 64? Because then I can get away with 64 bits, which is what we currently have in computer arithmetics. And so what we would do probably is we would just use powers of prime numbers that are smaller or equal than 64 until we have enough so that the 2 to the x minus 1s multiplied together give you numbers that have more than 200 decimal places. Okay, that's it. It's kind of interesting. I keep saying that I'm not a number theorist, I'm just playing one on this show, so some of these proofs are certainly something that are off the beaten path for me a little bit. You've also seen that in that one hiccup that we had in this presentation, but really, as I've talked my way through it, I can honestly say, swear and everything, that yeah, it all did make sense, except for that one little hiccup, and that is of course a stage that in a course like that we want you to reach also. We want you to go through these proofs and have every single step make sense. And in order to get there, well, again, it's time for you to do some homework, to do some proofs, to implement some of the algorithms. That's also a nice thing here. Quite a few of the algorithms are constructive, so as you do a homework problem with numbers, you will essentially automatically go through the proof, because the proof is what you do to get the solutions. All right, yeah, that's it for now. Have fun with the homework.